Our old friend, the meaning of multiplication. M times n equals p means we have m groups of n size for a total of p units in those m groups. So that meaning works perfectly fine when we have a whole number times a fraction. 3 times 3/4 is 3 groups of 3/4. So we have 3 groups of 3/4, which is just repeated addition, 3/4 plus 3/4 plus 3/4, which gives us 9 quarters total. 1, 2, 3, 4, 5, 6, 7, 8, 9, which is 1, 2, and a quarter. We can also think of it as part of an area. And this area, you're going to see we start to push against what if groups aren't wholes? So here, what I have is 1/2 of 3/5. I have half a group of 3/5. So first we start with 3/5. That's here in this left picture. And then if I split that whole thing in half, and that's why that bottom half is shaded, that part that is doubly shaded, let me actually go ahead and I'm going to be consistent. So first we have our 3/5, and then we took our half and shaded that, and that piece that was common to both, the part that's doubly shaded, represents our product, 1/2 of 3/5. And then we can see what that would be is we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pieces total, and 3 are doubly shaded, 3/10. And so we can see those are two of our models for multiplication of rational numbers. And so, right, going back to that first model, multiplication as repeated addition is a perfectly good interpretation for when we have a whole number times a fraction. So multiplication as repeated addition as whole number times a rational. We have 3 servings of sport drink. 2/5 of a liter is a serving. That means inside each of these we have 2/5, which is what this looks like. And to add that up, we have 1, 2, 3, 4, 5, 6/5, which is a whole and a fifth left over. So our area model works perfectly fine when we do wholes times parts. And then I've shown you one with as part of an area. So that was repeated addition. Here we have part of an area. So we have 2/3 of a serving, and there are 15 grams of fat in a whole serving. So how many grams of fat is there in 2/3 of a serving? Well, so we know that there are 15 grams of fat in a serving. And so they drew those in a nice, neat way. So it was already divisible by 3, which means that each of these is 1/3. So a third serving has 5 grams. And so if we put 2 of those in there to see what that looks like, we end up with 10 grams. So multiplication as part of an area doesn't work too bad when we have a fraction times a whole number. So notice how that's different than if I had 15 of something and each of them was 2/3. So things get a little bit different once we're looking at a rational times a rational. So consider, for example, if we have half of a serving, and we know that there's 3/4 cups in one serving, and we want to know, well, how many cups were in our half a serving? Well, here we start with half of a serving, and so that means the whole serving looks like this. should be the same height as this. And that whole can be split into 3/4 of a cup. So each of these are a third of a whole, but they're each 1/4 of a cup, right? So there's this external reference unit that's causing a little bit more work. And if we want to know how much is in half, well, we can just cut the whole thing in half. And we have a whole quarter, and then we have a half of a quarter. Well, if I have half of a quarter, I really have an eighth. So we have a quarter plus an eighth. And using our fundamental property of fractions, we have 2/8 plus 1/8 is 3/8. Because if we would just split this middle one, and so here I'm going to erase something real quick. If we would look at just this middle one, I'll use a new color. Here I have 3/4. If I split each of these in half, I end up with 6/8. And so half of those, this bit, is 3 of those 8s, which is what we got there, right? And so you can see how these images can help you not only set up your equation as we did way up there, but they can also to help you solve the problem directly by using the concept of fractions and multiplication. So normally every day, Monday through Wednesday, I have an activity that you guys work on your own. And then, or not on your own, but in groups, right? In class, we spend 50 minutes working through an activity. Well, Thursdays, unfortunately, we have our quizzes. And so there isn't time to make you do a group activity on Friday. I mean, I could have used 2 hours of class time, but that didn't seem worth it. So what I'm going to do for the rest of here is I'm essentially going to work through a couple class activities. And if you would like to work through them, because I highly recommend it, again, if we learn math by doing math, this is great practice, even in addition to homework. If you want to work through these, I'm going to post them to D2L so you can see them near the PowerPoints. There will be PDFs of these. And I highly encourage you to pause here and take some time to think through at least the first activity before moving on, just because I think this practice will be beneficial. So it says, for each of the rectangles below, fill in the blanks so you can use multiplication to describe the fraction of the rectangle that's shaded. You may assume that all lengths that appear to be the same really are the same. So first we have to look at what fractions are these wholes decomposed into. So if I look at it this way, I have 3/3, right? I have 1, 2, 3 of them. But if I look at this way, I have fourths. 1, 2, 3, and 4. And so what shaded is 1/4, 1, 2, 3, 4, 1/4 of 1/3. So 1/4 times 1/3 is, we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1/12 is shaded. And then here, so notice this is precisely our area model that we used for area way back in the day, last week. And it's the same area model we used earlier this week. But now what's happening is because both of our both of our factors being multiplied together are fractional parts, we end up with less than a whole shaded. So here we have 1, 2, 3, 4, so we have quarters. And here we have 3 out of 5. And these are quarters, so 3/5 of a quarter, or 3/5, 1/4. And so that means this one has 3, 4, 5. So we'd have 10, 15, 20 total pieces, 20 pieces total, and 3 of them are shaded. We have just 2 more of these to think through. Now, how do we have this one shaded? This way we have thirds. And this way, quarters. And now this piece, compared to this piece, is 1, 2 of 1, 2, 3. So we have 2/3 of a quarter. So 2/3 times 1/4 means that we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pieces. And we have 2 of them shaded, 2/12. And then our last one. And so these, I think, I could very well say, all right, tell me what is 1/3 or 2/3 times a quarter. And you would say, oh, well, that's a 1/6. Because you're like, well, that and that, a 1/6. Or I could say, here's a picture. Tell me what concept of fraction is shown. And the concept shown is the 2/3 times a quarter. Do the same thing here. We have 1, 2, 3, 4, 5 this way, fifths. We have 1, 2, 3, fourths this way. And so what is shaded? Well, let's go ahead and say we're starting with this piece. So of 3/5, 3/4 is shaded because we have 1, 2, 3 rows filled of 4 total. So that's 3/4 times 3/5, which is 9/20 because we have 3, 4, 5 in each row, 5, 10, 15, 20. And if I just drop these lines down, I have 3 times 3 is 9, or 9/20. And you can't see that below my head. Drag myself down a little bit. 9/20. And so see, you can start to see how when we multiply in this way, when we use our area model, our fractional parts intersect, and that common area to both is our result. So here it says, use the math drawings to explain why 1/4 times 1/3 is 1 over 4 times 3. So I'll talk about my meaning of definition. So first it says I have a quarter group of 1/3. So I have my whole, and here's my 1/3. That's my 1/3 that I talked about right here. And then I'm going to fill 1/4 of that. 1/4. So I have 1/4 of 1/3, which means I have this 1 filled of 1, 2, 3, 4, 8, 12 total. 1 over 12. And because that 12 comes from 3 times 4. Each row, my 3's, will have a group of 4 in it. So 3 times 4 gives me 12. And so when it comes to explaining why the product of two fractions is what it is, this is the sort of argument I'm looking for. First, show me the whole. Show me the part you're starting with, show me the part you're breaking it down into, and then show me your final result. And then recap by saying 1 is shaded. Oh, I went too far. Show me that 1 is shaded of the 12 total, so it's 1/12. And then here's another one. Use it to explain why 2/3 times 5/8 equals 2 times 5 times 3 times 8. Well, what we end up seeing is, again, we start with our whole, and then it says 2/3 of 5/8. So notice our second one always comes first, our 5/8. So our 5/8, and then shade 2/3 of it, which means we have precisely 1, 2, 3, 4, 5, 10 of 24. As it points out, multiplication of fractions just happens straight across the numerator and the denominator. So process, procedure, efficiency, multiply across the top, multiply across the bottom. Conceptually, think of groups of a size. We have 2/3 of a group of 5/8. So we start with 5/8, we take 2/3 of it, and we end up with 10 of the 24 final pieces that remain. And so now it says, use the definition of multiplication and math drawings to explain why 2/5 times 3/7, I wanted to make sure it wasn't the same, is 2 times 3 equals 5 over 5 times 7. So always start with a whole. That's my 1. 2/5 of 3/7. Well, we need 7s. 1, 2, 3, 4, 6. We'll pretend those are all equal. Equal sized 7s. 1, 2, 3 of those. So that is 3/7. And we have 2/5 of a group. And so what I'll do now is bring up another color. And it would probably be best if I would copy it over, but I'll go ahead and just put my 5th lines in. 1, 2, 3, 4. And we have 2/5 of a group. So we have this part here. And so how many are shaded? We have 2 columns and each of them has 3 in it. So we have 6 out of, but how many are there total? 1, 2, 3, 4, 5 in each row, 7 rows, 35. And again, 2 times 3 is 6, 5 times 7 is 35. And so this image shows us why it is true that multiplying across the numerator and across the denominator gives us our product when we multiply. But notice when we do addition, if we would draw a picture and we would use our models and put them together, this sort of multiplication doesn't happen, which is why when we multiply, our denominator changes, but when we add, it doesn't. And so those have all been done with fractions, but there's no reason you couldn't do this with a decimal. And so for this example, we have 1.6 times 2.4, or rather, let me be precise, we have 2.4 groups of 1.6. So groups, size. So here we have 1.6. Notice we're using our flats as 1 and our longs as, and our rods as tenths. And then, so we have 1 group, 2 groups, or 2.4 groups. We use our partial products. So here we have, and I'm going to rewrite this one over here. So we have 1.6, 1.4. And actually, if it's okay, let's just call that 2. If 2 and 2.6s is 1.2. 1.4 is a 0.4. And now we have 4/10 of 6/10. And if we look in there, you'll see that we have 24 little units. So we have 24 hundredths. So you can just write it as 24. So now what we have is 2 plus 1.2 plus 0.4 plus 0.24. Add down 4, 8, 2.84. And because that's not multiplication, that is addition. And because we have our handy dandy calculator, it never hurts to double check your work. So go ahead and pull out your calculator. Take 1.6 times 2.4 and 3.84. What did I do wrong? 2 plus 1 is 3, not 2. That's all. Just keep added incorrectly. And so I know this isn't a methods class, but let's think about it. So that was an addition mistake. That had nothing to do with the concept of decimal multiplication. And so when you see a child make an addition mistake, we have to be really careful at looking at what their work was. So for example, on this sort of one, there's no reason, say one of you did this on a quiz or a final, you would miss 1 point because you made a mistake. But your concept of multiplication is there, which is to say, if you did something that broke the concept of multiplication, like we had that example of, I think her name was Lizzie. Let me get back to my slide. Lizzie was multiplying, and what happened is she only counted this whole times whole piece, and then this part times part piece, and she missed the two others. So that would be worth of 2 points, right? Because that's a conceptual mistake. But thinking about what is important, what are we assessing, and here I care about, are you accurately reflecting the concept of decimal multiplication? And the answer is yes. Okay, division. So I think in terms of multiplication, it's less often we're going to see the repeated addition. We can use it, but I would say often use the groups of a size interpretation and your area model, and that will work whether you have whole times. So let me recap. That's a highlighter. Let me recap fraction and decimal multiplication. I would say generally speaking, use groups of, so blank number of groups of a certain size interpretation to set it up, and then I would use the area model. And it'll work always regardless of what you're working with. And so division, looking ahead, moving forward, how many groups? So remember back, so this is flashback to last week, week 2, we had our 2 meanings of division. How many groups and how many in a group, right? Those both corresponded to, if we had m times n equals p, we might not know how many groups there were, or we might not know the size of each group. And so we're going to, again, treat them both independently. First, for how many groups. So these activities are really some of the best. And I think fraction multiplication, or addition for that matter, is one of these ideas that really gets built up as being like the most difficult concept in K-8 mathematics. It's like dealing with these fractions, or dealing with decimals, or knowing where to put the point when we're doing decimal operations. What I really believe, and this is supported by research, is when students have a solid understanding of the concept of fraction, there will be fewer errors in the operations on fractions. And so much of this work goes back to, what is the meaning of fraction? What is the meaning of fraction? And we keep reinforcing it because this is how we support our students to be successful. And so here we have an example of 6/4 divided by 3/4. So it says, how many groups would be, how many servings of juice do you have if one serving is 3/4 a cup and you have 6/4 of a cup? Well, here is 1/3, and so there's 1/3 here, there's 1/3 here, and so when we divide that, we end up saying there are 2. So we could use, so there are 2. So how to use the math drawing to show that? Well, we know that there are 6/4 total, and we're going to split it into 3/4 pieces. And how many 3/4 pieces are there? There are 2. And so this is very similar to when we did, say, -15 divided by 3. I'm going to do -6 if that's okay. Divided by 3, -6 divided by 3. We have -2, -2, and -2, right? 2 of those red token or red chips goes to each circle. So looking at that, you can see really how this is the same exact process. It's this fair share of splitting between groups. So here's another sample student work. It says, Tanya and Chrissy are trying to understand 1 divided by 2/3 using the following problem. 1 serving of rice is 2/3 of a cup. I ate 1 cup of rice. How many servings of rice did I eat? So to solve the problem, Tanya and Chrissy draw a square divided into 3 equal pieces, and they shade 2 of them. So it looks like this. Now Tanya says there is, and so I'm going to use red for Tanya. Tanya says there's 1 2/3 cup serving in 1 cup. So there's my 2/3. And there's 1/3 of a cup left over. So the answer should be 1 and 1/3. Because there's a serving. So the 1 comes from here, and the 1/3 comes from here. And Chrissy says the part left over is 1/3 of a cup, so that is 1/3. But the answer is supposed to be 3 halves, or 1 1/2. Did we do something wrong? And so it says, please help Tanya and Chrissy. Well, what we see first is that there is in fact 1 whole serving here, right? We know they ate more than 2/3, so they ate a whole serving. So that 1 is there. And I agree that this is 1/3 of a cup. But what's a serving? So we have 1/3 of a cup, but a serving is 2/3. So how many of these make a serving? So how many thirds gives us 2/3? Well, it's 2. So this 1/3 of a cup is how much of a serving? So this 1/3 is half a serving. So we had 1 whole serving and another 1/3 of a cup, which is half of this. So we have 1 1/2 servings. And so it's important, right, that we think about what is our whole. In this case, the whole isn't a cup. The whole is a serving, which is 2/3 of a cup. And so it's important that we pay particular attention and look at that and see what is it that is going on. So that was the how many groups interpretation. The other interpretation is how many in a group. And so here it says, for example, there's 3/4 of a serving. How many ounces are in 1 serving? If 6/5 of an ounce are in 3/4 of a serving. So finish solving the problem in the example, then explain how to see the solution as multiplying 6/5 by the reciprocal of 3/4. So that is, why is it 4/3 times 6/5? Well, so we know that this amount, let me get my pen, 6/5 ounces. We also know that that's 3/4 of a serving. So if I line that up with a whole, if this is my whole serving, this should line up to 3/4, which it does. That means each quarter serving has 2/5 of an ounce. So we have 2/5, 2/5, 2/5, and 2/5. In each. So we have 4 times 2/5, or 8/5. But it says, well, where is 4/3 times 6/5 in all of this? Well, I did the equivalent of 4 times 2, which is 8/5, which means that my 4/3 times 6/5 must be somewhere in here. 1/3 is, and so this is this piece, 1/3 is, let me not put equals, 1/3 of a serving is 2/5 of an ounce. And we have 1, 2, 3, 4 of those. And I need to be precise because it's not 1/3 of a serving. It's 1/3 of what we were given, 1/3 of our 6/5. So 1/3 of what we had, of what we know, is that third. And how many of those thirds do we have? We have 1, 2, 3, 4 of them. So we have 4/3 times 2/5. But it's not 2/5, 6/5. So clearly of the two, I think the how many groups is a clearer interpretation. But we're going to work through a couple more examples because I think that this is worth our time. And like I said, I highly encourage you to work on this on your own in the PDF, just because we learn math by doing math. So here it says, write how many units in one group problem for 3 divided by 1/4, and explain how to solve the problem with the aid of a math drawing. So what we have is m times n equals p. This is our unknown. So we have 3 divided by 1/4 is the same as 1/4 times something equals 3. I gave each of my friends a 1/4 package of king-size Reese's. Again, still pretending that they have 4 in them. So I give each of my friends a 1/4 pack. I used 3 packs in total. How many friends did I share with? So I give a 1/4 pack to each person, or I used 3 in total. So how many was I able to give it out? I was able to give it to 12. So write how many units in one group for 1/4 divided by 2/3. We can start with our picture. 1/4, same whole, 2/3. And if it's okay, let me go ahead and switch that color. Two-thirds. And now let's go ahead and get a common denominator. Our common denominator is 12. So each of these gets split into thirds. And each of these gets split into quarters. And so our 1/4 becomes 3/12. And our 2/3 becomes 8/12. So it says 1/4 divided by 2/3. So how much of this fits in to this? Well, this bit is 8 long. TWEL F 12ths, 8 12ths, 3 12ths. So how many 12ths are there over here? There are 8. And how many of them go in over here? 3. So here we get 3/8. Because if we look at just this piece here, only 3 of these will fit up here. So 3 of the 8 will fit. And so to a how many word problem, I will leave that up to you guys. But this is the picture for it. And right, so see how drawing the picture from the very beginning, even when we're working with fraction divided by fraction, it makes it clearer to see what's happening. And so this is an extension of that exact process there. Here we have 6 divided by 6/5 divided by 2/5. And so it says consider these two. Explain in 2 ways why they must have the same solution. So here, if this is 2 and this is 6, well, use a different color. We have 1, so once, twice, 3 times. 6 over 2 is 3. But then, if these are fifths, that's 2/5, that's 2/5, that's 2/5, and that's 2/5. So now that's if each of these green things, fifth. So first we saw them as a 1, but now we see them as a fifth. And what we end up seeing is 2/5 and 6/5 is also 3. And so here it says, well, explain why we know. View 6/20 divided by 3/4. So 6/20 divided by 3/4. They want us to rewrite as our multiplication problem. We have some thing times 3/4 gives us 6/20. Well, we know we can multiply across the numerator and the denominator. So what times 3 gives us 6? 2. What times 4 gives us 20? 5. We have 2/5. But notice, that's the same as numerator divided by numerator and denominator divided by denominator. Because 6 divided by 3 is 2, and 20 divided by 4 is 5. So the second part, use the reasoning of part 2 to explain why this method works. Well, we know by multiplication that something times 3/4 is 6/20. And because we're now in the rationals, we don't have to worry about whether or not dividing gives us a whole number. When we move this 2/5 to the other side, when we rewrite it as our equivalent, we end up getting this piecewise division because, and this is a big because, we know that, let me call this unknown fraction AB, okay? So we have A over B times 3 over 4 is 6 over 20. That means A times 3 is 6, and B times 4 is 20. We can just use standard division, rational division. Divide both sides by 3. We get A is 6 over 3, and B is 20 over 4. 6 divided by 3 and 20 over 4. Because when we multiply across the numerators And because division is the inverse of that operation, we can just divide across the numerators and the denominators. So I'm going to save this one for you to practice because I think it's another useful sample to give you an idea of what's happening. And so, division of rational numbers. How many halves are in 3 wholes? Well, there are 6 of them. Because 2 of them make 1, 2 of them make another, 2 of them make another. That's a total of 6. How many eighths are in 3 quarters? Well, each of those quarters will have 2. And there are 3 of them, so there should be 6. 3 quarters divided by an eighth is 6. And so that work with the interpretations was really just getting us to think back to inverse relationship. But we can solve these directly sometimes by drawing a picture. So how many 3 quarters are in 7/8? Now it's a little bit harder. So I have my 7/8 marked, and I have my 3 quarters marked, which is really 6/8, right? So this 3 quarters is really 6/8. And so how many 3 quarters are in there? Well, 1 of them. And then this piece, which is, there are 1, 2, 3, 4, 5, 6 of them here. 1 and a 6th. So the bar of length 3 quarters is made up of 6 of these equal sized pieces of an eighth. And so there's at least that 1 in there, and then we put another one, we see there's another 6th. And so we have that 1 and 1/6. And so this is just your nice, neat typed up version of all of that work there. So pay attention to what your whole. Here, your whole is 3 quarters. We want to know how many of those 3 quarters fit. A whole 1 and then a 6th more. Dividing by decimals. There are lots of processes for dividing decimals. One's the standard algorithm. I would say one that works well generally in my mind is if we treat the whole and the part separately. So we have 128 plus 0.6 divided by 4. So something times 4 gives me 128. Should be 32. 32, 64, 64, 64 is 128. And what takes 4 to give me 0.6? What takes 4 to give me 60? 15. 0.15, 2 of those is 0.3, and 2 of those is 0.6. So my answer is 32.15. So that's one way we could do it. We can also do long division. And notice we'll get the same answer. So when our divisor is a whole number, when this thing out here is a whole number, that decimal point just comes up for the ride. Because we get our 128 divided by 4 was 32, and our 60 divided by 4 was 0.15. But that's not what happens when we don't have a whole number there. If we have, say, 0.32, our process doesn't quite work. And so what we can do is rewrite this as an equivalent problem. We're going to multiply both by 100. 32, or 0.32 becomes 32, and 1.2032 becomes 120.32. And now we can just follow that process of bringing that decimal point up and trucking along. And so our example. There are no 32s in 12, but there are some in 120. And so we can do our partial quotients with 32, 64, 128. So one more is going to be, what, 96? That looks right to me. So we can take 2 32s out. No, we can take 3 of them. Can't just take 2, we can take 3. Get 96. Subtract 4 gives me 100, so 24. 243, so 128. Two of those is going to be 256, so we want something a little bit smaller than that. Minus 32 is going to be 224. Is that right? So that should be 32. Calculator's not the enemy. We have 32 times. Nope, 32 times. It's 224. So bring our decimal point up. We can do 7. 224. 43 minus 24 is 6, and 13, so that's 19. 2. Let's see, 224, I have a feeling if I subtract 32 from it, is in fact 192. So that's 1, 2, 3, 4, 5, 6. 32's. 6, 192, subtract, we get 0. 3.76. So just like when we've introduced all of these models and representations and methods, it's important that children get to see all of them and choose the one that's most important for them. Or not most important, most useful, easiest for them to understand, most applicable. And so I want you to be familiar, you should know how to do the standard algorithm, but you should also be able to use our previous example where we divided our whole number and our decimal separately, which more or less appeared the same way in this division problem. And so in elementary schools, this process is often described as moving the decimal point 2 places to the right, which really is just when we multiply by both by 100. And we have that fundamental, so I want to make one more connection and then we'll be done for the day. If we have, I'm going to write this fraction in a way that we wouldn't see. We don't usually write decimals. 32.32 over 1.2032. Ooh, so I dropped my iPad. What we have here is a fraction. Our fundamental property of fractions said we could multiply by 1, and that 1 can look like anything we want. So I'm going to say that 100 is 100 100ths. And so that means that this 0.32 over 1.2032 is the same as 32 over 120.32. And so that's precisely why we can multiply both of those by 100 to move the decimal point. And we know from a previous exercise today that this quotient and this quotient will be the same. So recap. We looked at models, particularly the area model, for multiplication and division of fractions. Often when we're looking at dividing fractions, we're going to reinterpret it as a multiplication problem first, and then we'll use our fraction bar model to model it. But it's important that we pay attention to the whole, like in that 6th example where we were looking at our 3/4, and it's important that we make and we track the whole throughout this process. But as is often the case, if we go back to our concepts of place value and fractional parts, any of these procedures, we start to see the connections between the concept and the process that we follow. And so the homework will have quite a substantial amount of practice for these, because I think in terms of what we cover in this class, this is the hardest. Is that fair? Yeah, that's probably fair, because fractions just tend to be scary, but fractions are just numbers and decimals are just special fractions. And so we'll work through these together. So, all right, have a great day, everyone.